Wow, sounds pretty cool, right? What you just listened to was a low-pass filter sweep across a little beat that I made. Sounds pretty cool, right? Now let's consider the electrical circuits that could pull off an effect like that. What we have here on this diagram is a voltage source in series with a resistor and a capacitor, and the voltage is being read across the capacitor. Now if we want to know the voltage across that capacitor, we first need to consider the impedance of the capacitor, which we all know is 1 divided by j omega c, where j is the imaginary number, omega is the angular frequency of the voltage source, and c is the capacitance of the capacitor. Once we know the impedance of the capacitor, we know that impedances are essentially just complex versions of the resistance. So we can use a voltage divider to calculate the voltage across the capacitor. So we know the output voltage, VO, is going to be proportional to the input voltage, VS. And we know that VO has to be smaller than VS. So to get VO, we're going to multiply VS by the impedance of the capacitor divided by the total impedance of the circuit. We're essentially finding the proportion of the voltage that is absorbed by the capacitor instead of by the resistor. Then for the impedance of the capacitor, we can sub out ZC with 1 divided by j omega c, and then with some quick math we can make this a lot prettier. So multiply both the top and the bottom of that proportion by j omega c, and we'll get a nice clean equation that looks like this. Then we divide both sides of the equation by Vs, and we have an equation of VO over Vs equals 1 divided by j omega Cr plus 1. Now let's talk more about VO divided by Vs. VO is the output voltage and Vs is the input voltage, so the ratio between them is essentially telling us how strong the source voltage is at the output reading. If the ratio between them is 1, that means there is no difference between the output reading and the input source voltage. If the ratio between them is more than 1, that means the output reading is greater than the source voltage, meaning that there is some amplification going on. And if the ratio between them is less than 1, that means there is some attenuation of the voltage from the source to the output. This ratio will never be more than 1 because on the denominator there is always going to be something that's more than 1. You cannot get a negative number from the product of j omega c and r. For now, let's consider c and r as constant. So the only thing that can affect this ratio is the omega term, which is the angular frequency. So at different frequencies, we will see a different ratio for this equation. When omega is low, closer to 0, we will see that this ratio is getting closer and closer to 1. As omega gets higher, then we will see that this ratio becomes smaller and smaller. This means that higher frequency signals are much more attenuated than lower frequency signals. Now let's put this through a circuit simulator so we can see a small bode plot of this relationship. So as you can see on this chart, you can see that as the frequency increases, the level of attenuation also increases, as shown by the downwards curvature towards the right side of the graph, where the frequencies are higher. I'm focusing more on the dark purple line rather than the light purple line because the dark purple line represents the gain and the light purple line represents the phase angle, which is not really something we need to focus on for now. Now, what would happen to this relationship if we were to suddenly change the resistor value? As the resistance increases, the magnitude of attenuation for higher frequencies increases as well, and even lower frequency signals start to see more attenuation. Likewise, reducing the resistance also decreases the amount of attenuation that the different frequencies will see. We can make variable resistors with a little setup like this. Instead of a regular resistor, we have a resistor on a slider. If we slide the slider closer to the base of the resistor, we will see less resistance, and if we move it upwards, we will see more resistance. You could implement this type of circuit onto an audio fader like this, and then you're halfway to being a rockstar DJ. You can apply low-pass filter sweeps to your audio as demonstrated previously, and you can also apply these same concepts to implement many other types of audio filters. My favorite example of the use of a low-pass filter sweep in a song is the beginning intro section of Money Longer by Lil Uzi Vert. If you know any great songs that use low-pass filter sweeps, please comment them down below. I'd be very interested to hear them. Low-pass filter sweeps are especially common in EDM music because producers will often use this effect to slowly introduce the higher frequency signals to make those drops hit extra hard. Anyway, I hope you found this video entertaining and exciting and especially educational. I hope you have an amazing day. Thank you.